Welcome to Richardson RFPD's 2020 Virtual IMS demo on analog devices 30 MHz to 6 GHz integrated transceiver. My name is Larry Hawkins and I'm Director of Technical Marketing and Systems for Richardson RFPD. Our demo today is of the Adrv 9002, analog device's first integrated transceiver designed for the broad market. The Adrv 9002 has 2 transmit channels, 2 receive channels, and 2 synthesizers that can be muxed to any combination of the transmit and receive channels, allowing it to be used for FDD or TDD applications. Or you could even use one of the receive paths as a sniffer to see which frequency bands are not being used while the rest of the system is turned off, and then switch the whole system to the empty frequency band. It has various low power modes and the ability to do fast frequency hopping and DPD. I believe the first open market digital pre-distortion that works for very narrowband applications. It also has a SPI or LVDS digital interface, allowing it to be used with an inexpensive processor or FPGA. The Adrv 9002 also has various digital functions like digital down converters and FIR filters. And multiple Adrv 9002s can be synced together for MIMO type applications. Eval platforms and samples are available now, and the part will release at the end of 2020. The presenter for the Adrv 9002 transmit portion of our demo is Danny Malosian, RF Applications Engineer with Richardson RFPD.
In this slide, we present an overview of the D705, which is a 5-watt linear RF front end designed primarily for LTE low-band cellular applications, but it can also serve as a reference design for other applications, including military communications and public safety radio. The D705 features both a single-channel receiver with a high-performance LNA and a single-channel transmit chain that has roughly 57 dB of gain and delivers 5 watts of linear power at the antenna port with a nominal PA efficiency of 45%. The development kit for the D705 comes with a software GUI that allows the user to program settings for phase and amplitude for the onboard Doherty PA, as well as its bias settings. And as shown, there are multiple SMA RF connectors on board, allowing for full RF systems and component level testing and diagnostics. The next slide shows a block diagram of the demo that will run featuring both the D705 and Adrv 9002 integrated transceiver with DPD. The components in our demo from left to right include the Zinc 706 FPGA development board that has the Adrv 9002 transceiver eval board plugged in via FMC connector, a PC that runs both the software GUIs, the D705 hardware, a triple DC power supply, and test and measurement equipment to measure the RF output parameters. The PA output signal for this demo is measured just past the circulator and should be at a level of 39 dBm or better. Factoring in circuit losses, this equates to roughly 39.5 dBm or 9 watts at the PA and 5 watts after the duplexer. In this demo, we're looking to showcase the transceiver's ability to perform well with DPD in both wideband as well as narrowband applications. So we'll be using a 10 MHz wideband LTE waveform first, followed by a narrowband 1.4 MHz LTE signal. In both examples, we'll apply a linearization correction from the onboard DPD engine of the Adrv 9002 and see the before and after enhancements in ACPR performance. First step in the demo is to set up the PA on a D705, which uses a 2-stage LDMOS dual-path PA configured as a Doherty amplifier. So once we launch the actual GUI, we see this ADAM screen here, and ADAM stands for Advanced Doherty Alignment Module. This is an IC that's used on a D705 that helps us to adjust both the phase and attenuation settings for both legs of the Doherty amplifier for optimum performance. Once those settings are set, we switch to the AD7293 tab, which allows us to set the gate biases of the PA. These are 4 separate signals, and with the GUI, we actually have the ability to go down to 1 millivolt resolution on the gate bias to set the quiescent current. So once the PA is properly set up, we then move to the Adrv 9002 GUI. And in this GUI, there are many different options for configuring a transceiver. But once those are set up and programmed, we then move to the Transmit tab, load our file, and simply hit the Start button. And so for example, for the 10 megahertz wideband LTE waveform, on the top graph, we immediately see the FFT display for that signal. And on the bottom graph, the time domain representation. This signal is then going to be driven out to the D705 and used as a transmit input. So now we're looking at the output spectrum of the D705 with the wideband 10 megahertz waveform applied. This is centered at 790 megahertz, and it shows both the uncorrected waveform trace in yellow and the corrected waveform trace in blue. The transmit power level is about 39.2 dBm, which when we factor in post-PA losses, the actual PA power level is about 9 watts. As you can see, by applying the DPD engine of the Adrv 9002, adjacent channel power level is lowered to the minus 50 dBc range. So this is about 20 dB of improvement over the uncorrected waveform. Now we take a look at the narrowband 1.4 megahertz LTE signal before and after DPD performance. At a similar power level at 790 megahertz, you can see the improvement in ACPR is now down to the minus 50 to minus 51 dBc range, giving a little bit more than 20 dB of linearization correction.
At Next Gen RF Design, we are working with Richardson RFPD and Analog Devices to create a narrowband receiver demonstration for the Adrv 9002. The following demonstration uses the Analog Devices Adrv 9002 RFIC and HMC 8410 low noise amplifier. The FPGA processes IQ samples and streams over USB to the PC. The PC decodes public safety P25 radio signals and outputs the audio. The Adrv 9002 is configured as a wideband receiver, sampling up to 40 MHz of the UHF spectrum used for police and fire safety. The sampled IQ data is converted into multiple narrowband 12.5 kHz channels. The following shows the wideband spectrum along with active narrowband 12.5 kHz signals. The PC is set up to continuously monitor the control channel of a nearby trunk system. When user channels become active, the software decodes them and plays the audio. The wide bandwidth of the Adrv 9002 allows for multiple users to be decoded simultaneously while providing the performance required by a narrowband system. Let's listen in.
1323. 13. I have a VIN to try when you're ready. Go ahead. 1, F Frank, T Tom, Z Zebra, X X-ray, 8, William, 0, William, King Boy, 10609.
Tempo, what are you wanting with this VIN?
For optimal performance, the Adrv 9002 can be configured to receive a single 12.5 kHz channel with both DSP and analog filtering. Further, the high dynamic range receiver can coexist with adjacent channels by having over 150 dB per hertz dynamic range without using the AGC. And to avoid DC offset issues in direct conversion receiver architectures, a low IF mode is possible for narrowband signals.
Next Gen RF Design is developing a system on module, or SOM, with full transmit and receive capabilities using the Adrv 9002 RFIC and key peripherals. Contact Richardson RFPD or Next Gen RF Design for more information, or for design customizations. Vanteon Wireless Solutions is developing a 30 MHz to 6 GHz platform, including an RF front end, as well as a 915 MHz Wi-SUN network using the Adrv 9002. They are demonstrating the Wi-SUN network in their virtual IMS booth. Contact Richardson RFPD or Vanteon for more information or design considerations. We hope that you've enjoyed the demo. If you would like to learn more, please visit us at richardsonrfpd.com/analogdevices.